Okay, so where we left off yesterday was full statement of the Euclidean algorithm. So here it is stated um, completely in generality. This is exactly how the process goes. Um, Rather than actually writing out this proof, I thought I would go through the reasoning as to why this works, because the reasoning is exactly the same, and I'm going to leave it to you to actually fill in the details with generic R sub i's and Q sub i's here. But the reasoning works exactly the same, so starting from this bottom line and going back. But just to show you, again, how this reasoning was, because I know there's a little bit of confusion yesterday. So recall we had this example where this supposedly told me that the GCD of 123 and 456 was 3. Right? So how did this work? So the way that this worked was the following. So one, I work backwards. Okay, so I work backwards here and I say, okay, well, this statement here says a few things, but one of the things that it says is that directly, because this remainder is 0, it says that 3 divides 6, right? Okay, so this last line implies that 3 divides 6, but what else does this line say? We already know that 3 divides 3. Okay, so we already know that 3 divides 3. This line says that 3 divides 6. Why did I make the point of saying that 3 divides 3? Because the next line up has 15 written as a linear combination of 6 and 3. So I'm using that earlier proposition we talked about on first day of class, which said that if a number divides two numbers, in this case 6 and 3, then it divides any linear combination of those two. So 15 is a linear combination of 6 and 3. 3 divides 6, 3 divides 3. Thus, this tells me that 3 divides 15. Again, because I'm viewing 15 as a linear combination of 3 and 6. So I have 3 divides 3, 3 divides 6, 3 divides 15. Okay. What does the next line say? Next line says that 3 divides 36. And the reason why it says this is that I'm writing 36 by this line as a linear combination of 15 and 6, right? And since I know that 3 divides 15, 3 divides 6, this immediately tells me that 3 divides 36. Okay, now I'm going to stop for a second, and you might say, well, come on, it's obvious that 3 divides 3, 3 divides 6, 3 divides 15, 3 divides 36. You don't need this, right? But I'm showing you the process that gives you a completely general proof, right? If you follow this reasoning exactly with that general statement of the Euclidean algorithm, that's why this works. Okay, so this line, likewise, since 87 is written as a linear combination of 36 and 15, says that 3 divides 87. Continuing on, since this line is stating that 123 is a linear combination of 87 and 36, and 3 divides both of those, then 3 divides 123. Until lastly, since this first line, this first application of the division algorithm tells me that 456 is a linear combination of 123 and 87, this says that 3 divides 456. Okay. Now, question, what have I shown here? So I have shown that 3 is a common divisor of those two, right? But what is actually the reasoning behind 3 being the GCD? So recall we actually used the other example last time to show this, but the idea being that we've gone up, right, to show that 3 is a common divisor. But similarly, working down, I can arrive that any common divisor actually has to divide 36, 15, 6, and 3. How is that? How can I say that? Well, what I can do is I can say, well, if I have a common divisor of 123 and 456, right? Then, for instance, I could, so say D is a common divisor of 456 and 123. Okay. If it divides both of them, then clearly it divides any linear combination of the two. But look at this first statement. This first statement tells me that if I rewrite this a little bit, if I subtract, right, 3 times 123 from the right-hand side, what do I get here? I get that directly from this circled expression, I get that 87 can be expressed as a linear combination, 456 minus 3 times 123. Okay. And since D is a common divisor of 456 and 123, and since 87 is a linear combination of 456 and 123, what this means is that D must divide 87. Okay. If D divides 456 and 123, since 87 is a linear combination of those two numbers, D has to divide 87. So D is a common divisor of 456 and 123, so D divides 456, D divides 123. By this fact, it also divides 87. We just continue going down the line, right? So now, at this step, I write 36 as 123 minus 1 times 87. And now I have written 36 as a linear combination of 123 and 87. I know D divides both 123 and 87, so D must divide 36. Following the same rationale, next rewriting 15 as a linear combination of 87 and 36, I get that D must divide 15. And the next thing I get is D must divide 6. And then D must divide 3. So any common divisor must follow this pattern. Well, you don't have a lot of options here, right? So this is where it stops, right? This is the last thing I get because that's where this terminates. So I have shown that 3 is a common divisor. But more generally, any common divisor must divide 3. So what is the greatest possible common divisor? 3. GCD is 3. So that's exactly why the Euclidean algorithm works. The reasoning is exactly the same. I'm not going to write it out in general. That is left up to you all. So I'll put that back really quickly. There it is. All right, so that's the explanation for why that works. Now, I wanted to show a quick geometric interpretation of what it is that's going on. But before I do that, let me say the Euclidean algorithm is really, really nice. It is really, really helpful. One of the most immediate things that is helpful about the Euclidean algorithm. So remember, I had given an example of how one might find a GCD by factoring, but I said why that wasn't necessarily ideal because factoring for very large numbers can take a while. The Euclidean algorithm is actually pretty efficient. It's a pretty efficient and solid algorithm for finding the GCD. Theoretically, one of the best things that it does for us, though, if we're not thinking about, actually numerically writing out the GCD, figuring out the GCD of two numbers, one of the most important things the Euclidean algorithm does is by way of what I'm going to call the extended Euclidean algorithm, that's what the textbook calls it, it actually gives us a way of writing the GCD of two numbers as a linear combination of those numbers. Okay, and this is enormously useful. Okay, and we're going to have several immediate applications of that. But before I do that, I wanted to refer to a geometric interpretation of what's going on with GCD computation, and this is on page 25 of the textbook. So I figured there's no point in me drawing this when there's already a nice picture in the textbook. So what does this what is this picture telling me? So let's say that I want to find the GCD of 48 and 21. So maybe I'll write that. Okay. So I want to find, or I won't write it, I'll just refer to it. So let's, because it's right here in the box. So the GCD of 48 and 21. Let's say that I want to find that. All right. So plot 48 and 21 as point in the XY plane. So there we go. There's 48, 21. Draw in the line y equals x, so draw in that standard diagonal. Okay, so here's the line y equals x. Here I am, first quadrant at the coordinate 48, 21. I'm finding the GCD of 48 and 21. So what is the idea? The idea is what the Euclidean algorithm does is it takes, starting at this coordinate, and it moves to the left in increments of 21. So in increments of size 21, it moves to the left until I land on the opposite side of the line y equals x. So I move to the left in units of 21 until I cross the line y equals x. So boom and boom, right? And since I'm moving to the left, I'm moving in units of 21 in the x slot. So I would go from 48, 21 to 27, 21, and then to 6, 21, right? Okay. So I'm at the point 6, 21. This is the first time that I have crossed the line y equals x. All right. So after that crossing, I stop, and then I move down in increments of size 6 until I cross the line again. So since I'm moving down in the y slot. So I move down in increments of 6. So move down 6, that takes me to 15. Move down 6, that takes me to 9. Move down 6 one more time, and I am at 6, 3. So I've crossed the line y equals x again, and I stop. Now I'm at the coordinate 6, 3. Okay, now what I do is I move left in increments of 3 until I cross the line y equals x. Well, when I do that once, I actually end up on the line y equals x. And at that point, my algorithm terminates, and I can read off from either coordinate here, either x or y, because it lies on this line. I can read off the GCD, and that's 3. Okay, so what is it that this is actually doing, right? This is a nice picture of what's going on. What is it this is actually doing? So in every set of moves, as this is saying here, in every set of moves, the number of steps is actually the quotient in the step of the Euclidean algorithm. Okay, so the number of steps is the quotient. All right, that's your Q. And the remainder is how far you overshot the line. Right? So when are you going to wind up exactly on the line y equals x? Well, when you have remainder 0, right? Which is when the Euclidean algorithm terminates. So this is a nice way of thinking graphically about what it is that's going on. Okay. All right. So, moving on. Here's maybe what I will say, and then we'll get back to this. So, one of the most important things that the Euclidean algorithm does for us, that looks like two D's, that's a C and an L. One of the most important things that the Euclidean algorithm does for us is it gives us a way of expressing the GCD of two numbers a and b as a linear combination of a and b. So this is an important thing. Okay. The name of the method by which it does this is done via the extended Euclidean algorithm. Which is what I'm about to discuss now. Okay. Okay. So, what is it that we want to do? So what I'm trying to convey is that we can express the GCD of two numbers a and b as ax plus by for some integers x and y. Okay, you're going to see some applications of this to see why this is a very nice thing. Okay, so we can express the GCD of a and b as a linear combination of a and b. So there exists some integers x and y such that this holds. Okay, so we naturally want to find the x and y. Typically you're given the a and b, you want to find the x and y, right? So what is the idea? Let's revisit on a clean sheet this example we had already worked through. So this is the Euclidean algorithm done to compute the GCD of 123 and 456, right? So what is my claim here, right? So I want to express the GCD of a and b here. Well, maybe I should write specifically. I want to express the GCD of, say, 123 and 456, or it doesn't matter what order this occurs in. I want to express this as a linear combination. I'm going to write it in the other direction just because that's how it shows up in the textbook. So if you're following along in the textbook, you'll see the exact same thing. All right, so I want to express the GCD of these two numbers as a linear combination of those two numbers. So I want to find x and y such that this is the case. I already know the GCD is 3. So I want to write 3 as a linear combination of 456 and 123. Okay, so the question is, how do I do that from my Euclidean algorithm? Okay, so the idea is to take this Euclidean algorithm process, and where the word extended comes in is I want to rewrite this. Okay, so I want to rewrite this. So the idea is that I'm going to form a table. Okay, so I'm going to form a table. It's got 3 columns in it. In the first column, I'm just going to go ahead and put 456 and 123. Okay, in the second and third columns, I'm going to label those x and y. Okay, those are the coefficients, or those are the things multiplying 456 and 123 here. So I'm going to put x and y here, and the idea here is that my entry in the first column I want to think of as a linear combination where x and y describe what I have to multiply those things by for 456, for instance, to be a linear combination. What do I mean by that? So this is written out here. Entry in first column of my table. This entry in the first column I think of as 456x plus 123y. That's the idea. Okay. All right. And so what do I mean? My entry in the first column is thought of in this way. The idea is I want to write 456 as a linear combination of 456 and 123. Well, I mean, there's a trivial way of doing that, right? So I can trivially just, maybe I'll come over here and say 456 is trivially 456 times 1 plus 123 times 0, right? That's an easy way to make that happen. And what I'm going to do is I'm going to transcribe that to these two entries. So what this line in my table says is that one way to make 456 a linear combination in this fashion is to let x be 1 and y be 0, right? Similarly, 123 can be thought of as 456 times 0 plus 123 times 1. Okay, and so the entries here are 0 and 1. Okay. Now, here is where things get a little funky. Okay, so what is it that I want to do here? What I want to do is I want to try to fill in this table where the left-hand column, right, the leftmost column, contains entries that are my entries in this Euclidean algorithm process. So I want the next entry here to be 87. And so I want to think about 87 as a linear combination of 456 and 123. Okay, so how does this work? Well, remember when we did this proof of the Euclidean algorithm, we essentially did this. We did a version of this where we looked at this list and we said, yeah, there's an easy way to make 87 a linear combination of 456 and 123. I can look at this first line, right? I look at the first line and I can subtract 3 times 123 from both sides. So what I get here is that 87, just from this first line here in the Euclidean algorithm, 87 is 456 times 1, I'm going to write it like that, minus 3 times 123. Okay. Now here's where maybe some of the confusion can come in. Well, okay, so not here. It's going to be the next step where the confusion comes in. I can already fill out my table here with entries 1 and minus 3. Okay, so you might say, all right, I got no problem with this. I see how this is going to go. But I'm going to say one thing. Okay, so here's the caveat. We actually want to think about this in a slightly different way that's going to make this process more clear what it is that we're doing. So I'm going to rephrase this. 456, that's the first row in this table. So I'm going to call this is first row times 1, so that's really just the first row in my table. Minus 3 times 123, which makes up the second row. So this is minus 3 times the second row. Now, I can immediately transcribe that into the table as 1 and minus 3. It's not going to change anything, but you're going to see why in the next step this is going to kind of alter what goes into the table here, okay? The reason why, and again, you could be more careful. You don't have to do it exactly this way, but anything you do in this process to get the answer is going to be identical. It's going to be equivalent to what's going on here. There's really no other way to go about it. So, what next? So next, I take 36. So I take 36, not here. I take 36 here, the remainder when it first shows up as a remainder, and I can express, of course, 36, just like I did in my proof of the Euclidean algorithm. I can express 36 as 123 minus 1 times 87. Okay, but before I put that in my table, I'm going to think in this way. What is this really? This is 123 is the second row, so this is second row, minus 1 times 87, so that's minus the third row. So minus the third row. What do I mean when I say that? Second row minus the third row, this allows me to keep track of these linear combination coefficients without having to do something wonky here. What do I mean by wonky? So in order, what I would normally have to do to keep track of everything is, here I have 123 minus 1 times 87. I would have to plug in 87 as a linear combination of 456 and 123 into here. I would have to do that subtraction. I would have to group like terms in terms of 456 and 123 and then read off the coefficients. Now that's perfectly fine, but keeping track of it this way is actually more convenient than having to do that minor arithmetic. So here this is second minus third row. So second row minus third row, and I just do that subtraction. So 0 minus 1, that's minus 1. 1 minus minus 3, that's 4. Okay. So next in my table is going to be the entry for 15. I want to leave myself some room here, so maybe I can write. I think if I leave myself room here, I'll be able to do it. So let's look at 15 as it first shows up as a remainder. There it is. So 15 can of course be written as 87 minus 2 times 36, which I can interpret as 87, which is third row. So this is third row, minus 2 times 36, which is fourth row. So it's third row minus 2 times the fourth row. Let's just do this. So third row minus 2 times the fourth row. So that is 1 minus 2. So that's 3. And then lastly, I have minus 3 minus 2 times 4. So that's minus 3 minus 8. So that's minus 11. Okay. Continuing on. Okay, so next entry in my table, maybe I'll go ahead and draw this in so that stuff doesn't begin to run together. So the next entry, 6, first time it shows up as a remainder is here. So 6 is 36 minus 2 times 15. So this is 36, which is fourth row. 15 is the fifth row, so this is fourth row minus 2 times the fifth row, which I believe is going to work out to be, so this is fourth row is minus 1 minus 2 times 3, so minus 1 minus 6, that's minus 7. And then 4 minus 2 times minus 11, so that's 4 plus 22, so that's 26. Okay. And then lastly, I'll go ahead and write this out, and then I'm just going to do it. So 3, I can write that out as 15 minus 2 times 6. So that is fifth row minus 2 times sixth row. All right, you might think, why did the 2's come in? Of course, because that's the quotients in these steps. Okay, and so what does that end up being for 3? So that ends up being 17 and minus 63, okay, when you compute that. Okay, so what does this process tell us? So this says that 3 can be written as 456 times 17 plus 123 times minus 63. Okay. Now, if I had asked you to do that without the benefit of having the extended Euclidean algorithm, it's not at all obvious immediately to you probably how you could come up with these integers, how you could come up with 17 and minus 63 here. Okay. But this is an example. So this nice, fully worked out example is essentially all you need, okay, to make this work out. All right. Okay. So then moving on. What does all this tell us? So similar to what I did for the extended Euclidean, for the Euclidean algorithm, there's this theorem, which is, as I mentioned, one of the most important facts about the Euclidean algorithm. So let A and B be integers, at least one non-zero. Okay, so at least one of them is non-zero. There exist x and y findable via extended Euclidean algorithm. Okay, such that the GCD of A and B is AX plus BY. Okay. All right. So, what is the proof of this fact? The thing is that this could be proved most straightforwardly and kind of most intuitively by actually just I mean, I guess the kind of the most straightforward way of doing this would be to just work through this example that we did. Work through, I would say, the same reasoning, right? Use the same logic from this example, keeping track of indices, and you arrive at a proof of this. So there's actually a completely straightforward proof, but it's very annoying, and you've already seen that reasoning from the previous example, so it's adding nothing to it. So I'm going to give you a proof of it that is non-constructive. Okay, so unlike the straightforward proof, it's not constructive. It doesn't actually tell you how this works, but here's a proof of how it goes, and this might go back to your first course in proofs. You might appreciate a use of the well-ordering principle, because it's probably been a while since you used it. So let S be the set of integers that can be written as a linear combination of A and B. So let S be the set of integers that can be written in the form AX plus BY. Okay. Where, X and Y are integers. All right. Okay. So we're using the hypotheses of the theorem statement. Okay. So note that, as we saw previously, right, trivially, A, B, minus A, and minus B all belong to S. Okay. All right, so that's a nice thing to note, but why does that matter? Well, what we have done is we've said that A and B, at least one of them is non-zero. So if at least one of them is non-zero, I look at this list and I say, okay, at least one of A and B is non-zero. And whatever, let's say that B is the one that's possibly zero, right? And A is definitely not zero. Whatever A is, whether it's positive or negative, if it's positive, then A is a positive element of S. If it's negative, then minus A is a positive element of S. So I listed out all of these because regardless of whether A or B is zero, since at least one of them is non-zero, this list guarantees that S at least contains a single positive integer. Right? i.e., S contains at least one positive integer. Okay. Now we're cooking. We are good. So let D be the smallest such positive integer in S. Why can I do this? So I can do this by the well-ordering principle. So you can review that. It's in the appendix of this textbook. You can also view it or one of its many equivalent forms if you like. If you just use your search engine of choice to look for well-ordering principle, and you will see some version of it that will apply here. Okay, so since D is an element of S, D can be written as A, say, X naught plus B, Y naught for some X naught and Y naught that are integers. Okay. So the claim that we have is that A and B are multiples of D. Both of them are multiples of D. Okay, so D is a common divisor of A and B. Okay. Well, how can I show that? So proof of claim. Well, I can always apply the division algorithm. Okay, I can divide, say, A by D. So A is equal to, say, DQ plus r for some integers q and r such that r is non-negative and strictly less than d. Here's where this is going to come in. So if r is strictly less than d, why is that an issue? We've said that d is the smallest such positive integer that satisfies this thing that we want, that it can be expressed as a linear combination. So then what trickery are we going to employ here? We clearly want to say that r is also some linear combination, right? And we can do that using this expression for r. So but r is equal to a minus dq, which is a minus d can be expressed as this linear combination, of course. So this is a minus a x naught plus b y naught times q, which can be rewritten. So grouping terms, this is a times 1 minus x naught times q plus b times minus y naught q. So r is in S. Okay, but this implies r is equal to 0. Why? Because otherwise we'd have a contradiction. D, we've said, is the smallest such positive integer, but r is strictly less than d. So the only r that works and doesn't immediately yield contradiction is r equals 0. But if r is equal to 0, that is exactly what we need to say that d divides a, right? So d divides a. Similarly, d divides b. So d is a common divisor. Of a and b. All right, so it's a common divisor of a and b. So the quick finish here is to show that it is actually the GCD. Okay, well, so this is continue this proof. So let E be any other common divisor of A and B. Now, what we're going to do is actually a result of what we have just shown here. We're gonna restate this later because this is a very useful characterization of the GCD, which you might have already realized. What we want to say is that if E is any common divisor of A and B, it's going to turn out that actually E is going to divide D. Why? But D is a linear combination of A and B, right? Okay, it's kind of crowded, but there, that's actually too crowded. Let's rewrite that. So, but D, right, since by virtue of the fact that it is an element of S, D can be written as a linear combination of A and B. Okay? Thus, E divides D. Thus, E is less than or equal to D. Okay. So I've just shown that any other common divisor of A and B, I don't need the word other here, but I mean that's the implication, right? That's the worst case scenario thing that we're thinking about. The point is that for any common divisor of A and B, since D can be written as linear combination, E must divide it. But if a number divides another number, then this inequality is satisfied. But if E is less than or equal to D, where E is any common divisor of A and B, this implies by definition that D is the GCD of A and B. Okay. So by construction, it is a linear combination of A and B. So there exist X naught and Y naught that make this work. So that's it. That does it. Might seem kind of a roundabout way to go about it, but that's how it's done. So this last part of the proof, I should say this is, continued. This last part of the proof provides a nice, maybe slightly obvious application of the definition of a GCD, which is that the GCD is the common divisor such that any old common divisor of the same two numbers must divide it, right? So any common divisor must divide the GCD. Okay. All right. So that's a nice proof of that fact, and that fact is definitely useful. Okay. Actually, I still have plenty of room on this sheet. Okay. So a quick theorem, and then I'll be done with this section after a few corollaries and some propositions that kind of follow immediately from this fact. So let's state a quick theorem. I'm not going to give the proof. I will leave the details to you because it is very straightforward and it would actually be good practice for you anyway. You'll see what I mean. So let n be greater than or equal to 2, and let a sub 1, a sub 2, all the way up to a sub n be integers with at least one non-zero. Now you probably understand what it is I'm going to do. We hadn't really talked about yet the notion of common divisors of more than two numbers, right? So let's say I give you a list of integers. There they are. At least one is non-zero. And let's talk about the set of common divisors of all of them. Okay, well, the same conversation we had before applies here. It's non-empty, right? That's a non-empty set. It at least contains one, right? And so the same considerations as to whether or not talking about the GCD was ambiguous or not works here. We can compute the GCD of list of integers just as well, right? So then, knowing that we can compute a GCD for a list of integers just as well as for 2, right? There's no reason to stop at 2. We can likewise think about applying a Euclidean algorithm to those. You might not want to think too hard about it right now. Or an extended Euclidean algorithm. That's not what we're even going to use to get us across the finish line here. We are actually going to use the fact that we've used the Euclidean algorithm to prove that we can write the GCD as a linear combination, and then we're going to use the fact that we can write the GCD as a linear combination when you're talking about a list of two numbers to show it in the general case using induction. So that's the idea. So then there exists, so I'm not going to talk about any kind of Euclidean algorithm for a list, for finding the GCD of a list of numbers. Not going to do that. What we're going to do is cheat and use induction. So then there exist integers x sub 1, x sub 2, all the way up to x sub n, such that the GCD of that list can be expressed as a linear combination of that list of numbers. All right. And as I said, I'm not going to fill out the details of the proof. You can do that. I'm going to say induction. Induction. Okay. You can have a look at it in the textbook if you like, or it's more fun if you try to do it on your own, see how you think the induction would work. This is easier than trying to go through, constructing like a Euclidean algorithm or something. You can just use the fact that you know that it's true from this previous theorem for a list of two numbers. Okay. So, what are some immediate applications or corollaries from this fact, or from these facts? So one immediate corollary of the previous theorem, that is the one for two numbers, is if E is a common divisor of A and B, then E divides the GCD of A and B. Quick proof. D is AX plus BY for some X and Y, which are integers. And let's save us time. We'll say that we're calling the GCD D. So GCD is this linear combination. So E divides D immediately. Right. So this was the first thing we proved in the course, that if you well, basically, I think it was like the second or third thing we showed, which was if you divide two integers, then you divide any linear combination of them. So you divide A, you divide B, you divide linear combination, which is the GCD by this previous theorem. Okay, so this is the thing I was mentioning when I said this gives us a really nice characterization of the GCD, which is that the GCD is the common divisor that any other common divisor must also divide. Okay, so that's a nice fact. Next, here's a nice proposition that relates some of these things we're saying. So if A, B, and C are all integers, and the GCD of A and C is the same as the GCD of B and C, and those are pairwise relatively prime. Maybe I shouldn't say that they're pairwise relatively prime because I didn't say anything about A and B. So all we know is A and C are relatively prime and B and C are relatively prime. Okay, so then the GCD of AB and C is equal to 1 as well. Okay, so that product is equal to 1. So if you have A is relatively prime to C, B is relatively prime to C, then their product is also relatively prime to C. That's what this is saying. Okay, so how do we make this work? It would be a straightforward way of doing this if we had access to unique factorizations. That's the fundamental theorem of arithmetic. We're not doing that till a little bit later, so we will have an additional proof later. But for right now, we can actually do this immediately with this previous theorem about the GCD as linear combination. So since the GCD of, say, A and C is 1, there exist integers x sub 1 and y sub 1 such that 1 is equal to A times x sub 1 plus C times y sub 1. Okay. Similarly, also, since GCD of B and C is 1, there exist integers, say x sub 2, y sub 2, such that 1 is equal to B x sub 1 plus, x sub 2 plus C y sub 2. Okay. All right. So then what's the idea? The idea is to multiply these expressions. So 1 times 1. These are just two different creative ways of writing 1, but 1 times 1 is 1. So 1 is equal to that product. That's A x sub 1 plus C y sub 1 times B x sub 2 plus C y sub 2. Okay, and when I expand this out, what do I get? So after judiciously sorting this expression in terms of A, B, and C, what do I get? I get AB times something. That something, if you're interested, is x1, x2, plus C times something. And that something, if you're interested, is B, y sub 1, x sub 2, plus A, x sub 1, y sub 2, plus C, y sub 1, y sub 2. Okay, so after sorting, I get something like this. Okay, why did I write it out in this way? Specifically because I'm trying to say something about A, B, and C here. Okay, so the point is that if I look at this and I say, okay, I have written A, B, and C as a linear combination, and it turns out that linear combination is 1. What does that mean? Using, this old theorem that we've used a million times now, any common divisor of A, B, and C must divide any linear combination of A, B, and C. In particular, it must divide 1. Well, if any common divisor of A, B, and C must divide 1, then there's only one option for its GCD, and that its greatest common divisor must be 1. Right? So that's it. Okay, so this is a nice way of proving this fact without referencing prime factorizations at all. Okay. All right, so two other propositions whose proofs are more or less immediate. I'm going to leave those to you. Here's a quick proposition. Let A, B, and C be integers with, we'll say A specifically is not 0, and we'll say the GCD of A and B is 1. Okay. If A divides BC, then A divides C. Intuitively, what is this saying? So intuitively, this is saying that if A and B are relatively prime, and you know that A divides a product of B with some other number, then the fact that A and B are relatively prime tells you that B is not contributing much to whether or not A divides this product. In fact, A dividing this product more relies on C, the thing you're multiplying. It's the thing you're multiplying B by. Okay. So if you think about that for a second, that might be more or less obvious to you. I said I wasn't going to give the proof, but I might as well. It's very short. So note that 1 can be written as a linear combination of A and B for some x and y, which are integers, right? That's from the fact that these are relatively prime. Okay, well, I can actually just multiply by C, right? I multiply both sides of this by C. You're going to do this a lot in number theory proofs. You're going to do very similar things here. So multiplying both by C, what do I get? I get ACX plus BCY. Well, since A divides C and A divides BC, then A divides C. Oh, but that's what I wanted to show. Okay. So then the one question remains here, how would you know to proceed with the proof like this? Okay. So the way that you would know to proceed with the proof in this way is, what are you trying to show? You're trying to show that A divides C. You've used the fact that you can write 1 as a linear combination of A and B here. This should hint to you that, oh, well, I want to express C as some linear combination where I know the divisibility properties of both terms, right? Here, A divides, oh, wait a minute. This is stupid. This would be circular, right? I can't say that. I can't say that A divides C. This is wrong. Well, I didn't need that, though. I just need A dividing A. Right? So there we go. Now we have a hope of being right here. Okay? So A divides A, and A divides BC. So A divides this term, A divides this term, thus A divides C. Okay. All right. Okay, one more proposition that I'm done with the applications of this fact. So here's another. So let A, B, and C all be integers with A and B non-zero, and GCD of both A and B, again, is 1. Okay. Then if A divides C and B divides C, then AB divides C. What is this saying? Well, it's that if you have relatively prime, so think about it for a second. A and B have no factors other than 1 in common. Okay, and you know that A divides C and B divides C. If you're thinking in terms of, I'm off the screen, there we go. So if you're thinking in terms of prime factorizations, I know that we're not using that machinery quite yet. If you're thinking in terms of prime factorizations, it's that you have some prime showing up in A, right? But in B, there's no commonality there. So the point is that A and B dividing C individually must contribute primes in such a way that their product would still divide C, right? You don't end up with some situation where, you would have multiple copies of a prime in one of the factorizations and maybe only one copy of the prime in another, because then the GCD wouldn't be 1 in the first place. So that's what's going on. And again, why does this work? It's same. You get to see the power of this application here. So AX plus BY is equal to 1 for some X and Y. All right, so there exist integers X and Y such that AX plus BY is equal to 1. All right, again, multiply by C. So what do I get? I get ACX plus BCY is equal to C. Okay, that's just directly from multiplication by C. Well, what do I know here? Well, since B divides C, so since B divides C, what has to happen? AB must divide AC. That's a simple fact. I didn't even look at this expression. I can say that here. Okay, but knowing that, since A divides C, BA divides BC. But C is a linear combination of AC and BC. So AB divides AC, but BA, which is also AB, right, divides BC. So AB divides C, since it's written as a linear combination of those two things. And that does it. Okay. So you got to see multiple ways in which this game was played, right? Okay. So that is all I wanted to say about the applications of this fact that the GCD can be expressed as a linear combination of the numbers itself. Okay, so what do I want to talk about next? So might seem kind of random, and again, you've no doubt seen this in some form before, but it's nice to see this because it allows you to ask number theory questions in other number bases, right? So let's talk about other number bases. And if we were in person, I would have a lot of fun playing the troll here by showing you some really funny, troll math stuff involving peculiarities in number bases and the classic 0.9 repeating equals 1 question, right? The non-trivial non-uniqueness of decimal expansions. But anyway, since we're not, I'll spare you that since I don't get to see your reactions in real time, so it's just not as fun. So we use base 10 obviously for a variety of reasons. It's not 100% understood why we use base 10 because people always talk about hands, right? You got 10 fingers usually. So, you know, it makes sense to use base 10. But of course, there were various civilizations that didn't use base 10, right? Babylonians, as I already mentioned, used base 60 for various things. And I think it was noted, I think it's said here, that the Mayans used, base 20, I think. So someone said maybe they use their toes as well as their fingers. And then, of course, there's plenty of other examples of using non-standard number bases for some amount. So one example is using, like if you're thinking of in units of measurement, right? In some might say the bad systems of measurement, you don't have nice conversions between different units. If you wanted to talk about, for instance, like stone as a measure of weight, saying that you weigh so many stone, right? If you're British or something, that's one particular thing that might seem a little not intuitive to use, groupings of like 14 or something. So anyway, though, but there's for a variety of reasons, of course, there's plenty good reason to use different number bases for different things. So let's just write out like I have the number 4,327, right? 4,327. So the fact that I don't include a subscript here means that I want you to read this in base 10. That's usually the convention, of course, we're always going to follow. If I really, really wanted to be silly about it, I would include the subscript there to say, yes, this is base 10. But of course, we're just going to say this is 4,327, right? Technically, the way that you should read this when you're thinking about other number bases is 4327, right? Because the thing that, of course, characterizes using a base B expansion for a number, so we're going to talk about base B expansions. So using a base B expansion for a number, of course, it's the thing that characterizes these sorts of things is place value, right? The digits have some place value. So if I were to scramble these digits around, use the same digits, but I scramble them around, right? So if I used 7324 or something, these, of course, even though I'm using the same digits, this definitely is a different number because these inhabit different places, right? And there's place value. So what is this really saying? This is saying, I'll write it in descending. So this is saying 4 times 10 cubed plus 3 times 10 squared plus 2 times 10 to the first plus 7 times 10 to the 0 is exactly this number that I'm talking about, which of course I can recognize. 10 to the 0, that's the ones place. 10 to the first is the tens place. 10 squared is the hundreds place, and 10 cubed is the thousands place, right? So, and of course, to avoid being really annoying, technically we could write zeros, right? An unending line of zeros on both sides of this thing, but of course we don't do that, right? We suppress that. And so here's the base 10 expansion for this number, right? But of course I can use other number bases. So here's an example, right? If I write, so in base 7, we'll say, what about like 3,524 in base 7? See, I already read that as 3,524, but that's base 10 language. This is 3524 in base 7. So what is this? If I wanted to figure out what number in base 10 this is, how would I do that? So in base 7, this is 3 times 7 cubed plus 5 times 7 squared plus 2 times 7 to the first plus 4 times 7 to the 0th power. Okay, so just writing this out, this is 3 times 343 plus 5 times 49 plus 2 times 7 plus 4 times 1, which ends up being 1,292. And if I really wanted to be technical here, I'll include the subscript 10 to say in base 10, the number 1,292 is the same thing as the number 3524 in base 7. Okay? All right. So again, you've almost certainly seen something very, very close to this, if not this sort of thing exactly. So this is just a different number base, right? That's how this goes. So this going in this direction, converting from some other number base to base 10 is easy. It's just a multiplication and an addition problem. What if I wanted to go in the other direction, right? So what if I wanted to go in the other direction? I.e., let's just give an example. So let's say convert the number in base 10, let's say 21,963 in base 10 to base 8. Oh, I don't know why I included parentheses there. Oh, because the C kind of looked like a parentheses. There's no parentheses here. Okay, so convert 21,963 to base 8. How do I do this? I use the Euclidean algorithm. You might think immediately, wait. How's the Euclidean algorithm going to help with this task? Well, I mean, let's think about it for a second. So let's just write this out first of all. So what do I do to write it in base 8? What I do is I continuously divide by 8. So continuously divide by 8. Sorry, I shouldn't say why did I say Euclidean algorithm? I meant the division algorithm, not Euclidean algorithm here. So the simple division algorithm, we're not talking about GCDs. There's no Euclidean algorithm showing up. That was me misspeaking. So the division algorithm here is just quick application of continuously dividing 21,963 by 8. So let's just do this step by step. So 21,963, when I divide by 8, what do I get? So the quotient is 2,745 times 8. The remainder is 3. Okay, now I divide this quotient by 8. So when I say continuously divide by 8, I mean I divide once by 8 and then I divide the quotient by 8, right? So 2,745 divided by 8 again, the quotient is 343 times 8, and the remainder is 1. Okay, again, I divide the next quotient by 8. So 343 is 42 times 8 plus 7. Okay, next, I divide the quotient 42 by 8. I get 5 times 8. The remainder is 2. Okay, and then lastly, I divide this last quotient by 8. Well, 5 is 0 times 8 plus 5. Okay. Now, how do I get the base 8 number for this thing? I read the remainders backwards. So 21,963 in base 10. What is that in base 8? It is 52713 in base 8. I read the remainders backwards. Why does this work? Why does it work out like that? Well, I just continuously expand these things. So I'm going to use these boxed lines here for a second. So using those, maybe I'll put those here. Okay, so there. Oh, running out of room. Okay. All right, there's the box. Okay. All right, so using this, I can note that 21,963 is, by that first line, it's 2745 times 8 plus 3. Okay. Now, what I want to do is use the second line to substitute in for 2745 that expression, that linear combination, or rather that division expression. So this is 343 times 8 plus 1 goes in the slot of 2745, and that is times 8 plus 3. And now you might already see exactly how this is going to work, but I'm going to go ahead and do it all the way out. 343 likewise can be, I can substitute in for that expression, the third line. So this is 42 times 8 plus 7 times 8 plus 1 times 8 plus 3. Okay. All right. Next, I do the same thing with 42. So this is 5 times 8 plus 2 times 8 plus 7 times 8 plus 1 times 8 plus 3. Okay, let's stop here and keep track of all of this stuff that I've done here. So what do I have going on here? Okay, so I have 8 times 5 times 8 times 2, so that is 5 times 8 squared plus 2 times 8, right? Plus 7 times 8 plus 1 times 8 plus 3. So I haven't finished here yet. So what am I saying this is? So then this is 8 times 3 here. So this is 5 times here this is 5 times 8 squared plus 2 times 8 plus 7 times 8 plus 1 times 8 plus 3. So this is here 5 times 8 cubed plus 2 times 8 squared plus 7 times 8 plus 1, and all that is multiplied by 8 plus 3. So again, what do I get here? So this is 5 times 8 to the 4th plus 2 times 8 cubed plus 7 times 8 squared plus 1 times 8 plus 3. Okay. All right. And so what do I get here once I write this as 8 times 0? I get the base B expansion, right? So this is 5 in the 8 to the 4th slot, 2 in the 8 to the 3rd slot, 7 in 8 squared slot, 1 in the 8th slot, and 3 in the 1s slot. Which is exactly the same as if I had just read the remainders off backwards and been done with it, right? But that's why it works. So now you see. Okay, so you can do this with any number base you like. A couple other number bases, of course, of note are binary, right? So you could convert a base 10 number to base 2. You already know that binary is useful for computing. Another number base that's interesting for computing, and it's also interesting for us because it's a number base that's larger than 10, is hexadecimal, right? So hexadecimal is a perfectly valid example of another number base that's useful. So that's hexadecimal is base 16. But then you should think of a few things immediately, right? So there's some practical things to think of when you're thinking of other number bases. So one, we did a couple of examples, so base 7 and base 8 here. Both of those were less than 10. What do you notice about the digits, right? So whatever the base is, that's how many digit symbols you have that can possibly go into any particular place, right, or any digit slot, right? So in base 7, there are 7 possible digits, right? What are those possible digits? Well, 0, 1, 2, 3, 4, 5, and 6 if we're using the same symbols that we use in base 10, right? 7 is not a symbol in base 7, just like 10 is not a symbol in base 10, right? In base 10, you need 2 digits to represent 10. You need a 1 and a 0, right? So there is no symbol for 10. We reuse 1 and 0. So in base 7, 7 is not a symbol in base 7. It's the only digits that are allowed are 0 through 6, right? That gives you 7 digits. Same thing in base 8, right? So just looking quickly, you already know that you're wrong if you have a digit that is 8 or higher here. So then we don't need any extra symbols or anything if we're dealing with a number base that is 10 or less, right? Because we already have the symbols that we have from base 10. But what happens if you're dealing with a number base that's base 60 or base 20 or base 16 in the example of hexadecimal? So, well, if you have a number base that is larger than 10, because we don't readily have digits available for those, we have to use symbols. So, for instance, in hexadecimal, what's used are the letters A, B, C, D, E, F. Okay, so those letters fill the role of the missing digit symbols, right? So that means how many, what are the possible numbers of digits that can potentially go in a single digit slot in hexadecimal? 16, right? 16 is the number. So you have 0 through 9, and then you have A, B, C, D, E, F, right? Those are the slots, for instance. Okay, so I won't get back to other number bases for a bit. So in closing, I have a few minutes left, and I'll finish up this discussion tomorrow. But quickly, I just wanted to start with the discussion of Fermat and Mersenne primes. So Fermat and Mersenne primes. I guess I should call them Fermat and Mersenne numbers first, although we are interested in these numbers specifically when they are prime. Okay, so what's the idea here? Because the role that prime numbers play is obviously very important when you're studying integers, naturally humans have been interested in finding the largest possible prime number since antiquity, right? So we went through the proof that there's infinitely many primes. So since there is no largest prime, of course, we will continue to find larger and larger primes necessarily. But it's interesting to be at any given point in time to know what is the largest prime number that's been found. Right? That's an interesting question in and of itself. So many hundreds of years ago, it was realized that there are some expressions, of course, that generate more than one prime, right? So there in general were algebraic expressions that generated some primes. Maybe they only generated one prime, but the idea was that if you're thinking about, say, really, really large primes, then it might be natural to look at exponential expressions because you know that exponential expressions grow really rapidly, right? And so since they grow really rapidly, it would make sense that if you were able to find an exponential expression that generated primes, at least for some values, then it would be a nice thing because those primes would grow really rapidly. So you would have a high likelihood of those primes being fairly large. Okay, and so the first example of this that was kind of thought up, well, and I mean, they're named Mersenne numbers for a French guy who wrote them down, but they actually have been known about since antiquity. I mean, they've been known about a long time. They actually even showed up in Euclid's elements. So primes of this form have been known about for a while, but Mersenne's the first that actually noticed that this particular form generates a rather large number of primes. So you look at this expression and you immediately say, okay, when are these things prime, right? So like when are these things prime? It turns out that they're not always prime, right? You can immediately come up with, say, for instance, note, right, that 2 squared minus 1, well, that's 3. That's prime. Okay. 2 cubed minus 3, that's 7. That's prime. Okay. 2 to the 4th minus 1 is 16 minus 1, so that's 15. That is not prime. Okay. So already here you notice that this is not prime. Just going forward a little bit, 2 to the 5th minus 1 is 32 minus 1, so that's 31. That's prime. Okay. 2 to the 6th minus 1, what is that? That is 64 minus 1. That's 63. That is not prime. Okay. Next, I have 2 to the 7 minus 1. So that's 124 minus 1, so that's 123. That... Wait a minute. What should I... Oh, 128. No, this is 120. What am I doing? This is 127. Okay. That's 127. And that is prime. Yeah, that's prime. Okay. All right, so... you look at these and you say, all right, well, for all of the prime exponents, these were prime, and for all the composite exponents, these were not prime. Okay. It is going to turn out, and I'll do that at the beginning of class next time, that when these are composite, when the exponent's composite, they're definitely not going to be prime. But they're also not going to be guaranteed to be prime whenever the exponent is prime. Okay, it's just that the exponent being prime is required for these Mersenne numbers being prime. Anyway, so this is a good stopping point, so I'll end the lecture now, and tomorrow in class we'll continue and we'll finish chapter 2. So I think that's about it.